So what I'm going to talk about is mostly Cologne internal work. So down here you see my collaborators. So these 4 people are from Cologne. So Kevin O'Brien is a PhD student in my group. Latza is a postdoc in my group, and these 2 people, Achim and Simon, these you must probably know. And the only non-Cologne person is the guy here on the left, that is Masahiko Yamada. He is a PhD student of Masaki Yoshikawa in Tokyo. I'm going to talk about a certain type of spin liquids. So let me first explain what I think about when I think about spin liquids. And let's be a little bit more concrete than this picture where it just spins floating around in a liquid. So what is a quantum spin liquid? Well, it has certain properties that we have to require. The first one is we do not want to have any magnetic order. So magnetic ordered state we would call a quantum spin solid. So no magnetic order. We don't want to break any symmetry of the system spontaneously. And we also want the spins still to fluctuate. We don't want to consider a, so to say, trivially disordered state where the spins are just frozen in random positions. We really want spins fluctuating even at 0 temperature. And last but not least, we also require something that we call spin fractionalization. We want a spin degree of freedom to basically fractionalize in smaller parts. In our case, these parts will be a Majorana fermion and emergent C2 gauge field, but the spin fractionalization can take many different disguises. Now, when you look at this list here, it's actually a pretty vague list. There's not like one feature where we say, okay, if you have this, you have a quantum spin liquid. And that is a generic problem in this field. We basically don't, at least if you think of experimentally accessible features, we don't have one feature that basically tells us, okay, if you have this, declare victory. So you all know in fraction quantum Hall states, if we measure the Hall conductance or the Hall resistance, if it's quantized, we can declare victory. We don't have such an experimental probe in quantum spin liquid. In theory, it's a little bit better. In theory, we have something that is called long-range entanglement. So that is something that we can measure in numerical simulations. And it tells us something about if we spatially bipartition the system in something that is we call part A and part B, then part A and part B are entangled with each other in a non-trivial way. This we can measure, and if we find out that the state indeed is long-range entangled, then at least theoretically we can declare victory. Mostly what we look at experimentally are these features up above. But if you really want to have to say a solid definition of quantum spin liquids, then usually we use the last feature here. Okay, so that is what I think of when I think of quantum spin liquids. So how would we get quantum spin liquids? Well, the first thing we need to do is we need to suppress magnetic ordering. And usually we do this by frustrating the system. So what you see here is basically a lattice of corner-sharing triangles. On each corner of the triangle I have a spin. That's for simplicity assume it's an Ising spin. And we look at an antiferromagnetic interaction. So this spin we put down, this spin wants to point up, and this spin is frustrated because it doesn't know where to point. And if you look at this lattice, you realize a lot of these spins will be frustrated. They will not know what to do. And that leads to a huge or macroscopic ground state degeneracy in the classical system. And if you then look at quantum fluctuations, then quantum fluctuations can do anything. And they can drive the system into an interesting quantum phase. Now it's on mute.
Ah, okay.
It's not working?
Sorry.
Wait, let me do it like this. Okay. So, let me do it like this. Okay, so that is geometric frustration, and it's one of the main driving forces for getting quantum spin liquids. So one of our best candidates currently for a quantum spin liquid material is this Hermanns-smithite, where the magnetic sides form this Kagome lattice. So on each side you have spin 1/2 degree of freedom, you have Anderson and Heisenberg interactions. And this is really one system where we believe the ground state should be a quantum system. So this is very interesting, but it's not what I'm going to talk about. I'm going to talk about another way of frustration, which we call exchange frustration. And what we're going to look at is a system with spin 1/2, so the spin 1/2 sitting on these white blobs here. And each spin has 3 nearest neighbors. And with each nearest neighbor, I look at the direction, so I want to align one. Physics, so this is what we generically call the Kitaev honeycomb model, because Kitaev introduced it on a honeycomb lattice. And he showed that this interaction really has interesting quantum spin liquid phases. And this model is really one of our most important theoretical models because we can solve it exactly. We know exactly what is happening. We can compute all the properties rigorously. The downside, of course, is that you look at this interaction and it looks very artificial. It doesn't look like something you can easily get in a material. Fortunately, that's not true. We have a material class where we believe that we do have Kitaev interactions dominantly in the material, and one of these is certain types of iridates. Next slide. So let me give you a brief overview of why we think that these Kitaev type interactions can be dominant in materials. And this was work that was pointed out both by Ginyard Kalaludin and George Jackley. And in order to get Kitaev interactions, you need really several different mechanisms to conspire. So what you first need is a very particular microscopic structure. So you want the iridium atom, that's the magnetic side, you want it to be surrounded by 6 oxygens that form this octahedral structure. And this octahedral field will split the degenerate orbitals for the iridium atom. Iridium is quite heavy, so you have a large spin-orbit coupling, which further splits the orbitals. And it splits them so far apart that even moderate electron-electron correlations can drive you into Mott insulator phase. So at the end of the day, what you get when all these conspire is you get a Mott insulator, which has an effective spin 1/2 degree of freedom, but it's not your pure spin, it's spin orbit entangled. So this spin knows about direction. So this spin really can have a direction-dependent interaction. So what interaction you do have depends a lot on how these octahedras are arranged with respect to each other. So one way of arranging them is this corner sharing arrangement. So you have an iridium atom here, another iridium atom here, so these are the magnetic sides. So the orbitals, they're d orbitals, they're quite close to the iridium atom, so there's hardly any direct overlap. So most of the exchange interaction goes via the oxygen here. Here, say you have a single exchange path. This single exchange path gives you a Heisenberg interaction if you do the calculation. You can have other microscopic arrangements. So one interesting is this edge sharing arrangement or parallel edge sharing arrangement. And the important feature here is that you have two exchange paths. So this iridium atom is connected to this one by this upper path and by the lower path. And these two exchange paths, they interfere destructively, which basically kills your Heisenberg interaction. And the interaction that is left is the Kitaev interaction. Köln and Jacqueline, they didn't just explain that this arrangement could give you a dominant Kitaev interaction, but they actually really proposed a class of materials. And what they proposed is iridates, both sodium iridate or lithium iridate. And for both these materials, we have now found that indeed Kitaev interactions are the dominant interaction. I'm going to focus on lithium iridate because it's a very interesting compound. So the first iridate compound that was found by the Gegenwart group was what we now call alpha lithium iridate. So the blue atoms, again, these are the magnetic sites, these are the iridiums. You see they form this nice honeycomb structure. So the material is layered honeycombs. And on the left-hand side, I indicated how the oxygens are placed, and you see you have a really perfect edge-sharing octahedral structure. And people were very interested in this because this gives us the first material that really realizes a Kitaev-like Hamiltonian on the honeycomb lattice. And in fact, you don't have just lithium iridate, but you also have sodium iridate and ruthenium trichloride. So there's a lot of experimental study going on for these three materials. Now, lithium iridates are especially interesting because you don't just get honeycomb lattices. You also have two other lattice structures you can get, and these are called beta and gamma lithium iridate. It's just a numbering scheme. And the interesting feature here is that these lattices are truly three-dimensional. They're not layer two-dimensional, but three-dimensional. And I realize these lattice structures are quite hard to look at when you see them for the first time, so let's focus on the important features. The important feature is if you look at an iridium site here, it still has three nearest neighbors. And you see there's really there's perfect 120-degree bond angle between them. So that's the first thing, it's tricoordinated. The next feature is you still have this edge-sharing octahedra structure. So this now gives us materials that should realize the Kitaev model on a three-dimensional lattice. And we realize we already have two different three-dimensional lattice structures that we can consider. And that is really the point where we got interested in it in Cologne, because we wanted, well, we have already two lattices. How many more lattices are there around in 3 dimensions that are tricoordinated and that would have interesting physics? And then, of course, well, we're talking about spin liquids. Should the lattice actually matter or not? So, fortunately, both questions you can answer positively. There's a lot of tricoordinated 3-dimensional lattice structures in there. And the spin liquid does care about the lattice. So here you see an arrangement of different tricoordinated lattices. It's not a complete list, it's just the most beautiful lattices we found. And you can organize them. These lattices have been classified. They have been classified by A.F. Wells in the 70s. And he used 2 numbers to classify them. The second number here, you see that is simple. That just means you have 3 nearest neighbors. The first number tells you what is the smallest loop in the lattice. So if you look at a honeycomb lattice, you see the honeycomb plaquettes have 6 bonds in them. So this lattice you would call 6, 3, and that's the only lattice in 2 dimension that has this feature that all the loops have the same length. If you go to 3D and longer lattices, you get a variety. So then we usually call them something like 10, 3, and then we enumerate them from A to whatever. This lattice here, that is 10-3b, or the hyperhoneycomb lattice. That is the one that is realized in Iridates. Other lattices like this lattice or this one, we actually believe we can realize in a completely different setup, namely using metal organic frameworks. And also metal organic frameworks should have dominant Kitaev interactions. Okay, so now we have the lattices. Let's assume we can realize them. Let's assume there is dominant Kitaev interactions and just see what kind of physics can we get. And so let me give you a 1-slide crash course on how to solve the Kitaev model. And if you want to know more, then I really recommend you to go to the original paper by Kitaev, because it's a very nice paper. It has 100 pages, but only the first 30 are basically relevant for the Kitaev model. All the rest is conformal field theory. Okay, so here you see a small part of a tricoordinated lattice. So we have 3 different types of bonds. That are the 3 colors here. And we assume that we have, depending on the bond type, we want to align the x, y, or z component of the spin. So we start with this Hamiltonian, and it's a highly frustrated Hamiltonian. So usually we would think it's completely useless to try to solve it exactly, because it's, or even numerically, it's in general, these Hamiltonians are also very hard numerically to solve. But let's follow Kitaev, and the first thing Kitaev did is he splits each spin apart. Now this is generically a good thing to do because we want the spins to fractionalize. So at the end of the day, we want to split the spins apart so that we write them in terms of the true quasi-particles of the system. Okay, so what we do here is we write each spin components in terms of 2 Majorana fermions. So in total, we introduce 4 Majorana fermions. I indicate them here by the colors. So you have 3 Majorana fermions that you call AX, AY, AZ, and then 1 remaining which we call C. You will realize in a second why we do that, because we want to rejoin them again. We don't want to write everything in Majoranas. So we will introduce a new operator, a bond operator. So this combines 2 Majoranas of neighboring sites, and this operator lives on a bond. So this is sketched here. So this bond operator, if you look at it, you will realize it's a Hermitian operator. It has eigenvalues plus and minus 1. So this Hermitian operator defines you an emergent Z2 gauge field on the bonds. And now you basically have rewritten your Hamiltonian into something like this. So you have a Hamiltonian of an emergent Z2 gauge field, that's the U's, and they interact with the Majoranas. Okay, so up to now I have just done mathematics. I have done, so to say, an exact mapping of a spin Hamiltonian to this Majorana Hamiltonian. And I basically rewrote a complicated Hamiltonian into another complicated Hamiltonian. So because this is also something that we in general will not be able to solve. And now here comes the magic of the Kitaev model. The magic of the Kitaev model is that this gauge field here is not dynamic. In fact, it's static, and in most of the cases it's also gapped, which tells us that if we're interested in low energy features, we can simply forget about the gauge field. We put ourselves into the gauge configuration that has the lowest energy, and then the only thing we have to care about are the Majorana fermions. And now, so basically what we're allowed to do, we are simply allowed to replace these U's by numbers. And then we're left with this Hamiltonian, and this Hamiltonian is a free Majorana Hamiltonian. That is pretty simple to solve, and even our bachelor students can do that. So at the end of the day, I want to stress two things here. So first of all, I never did any approximation. So the magic of the Kitaev model is really that we can write a strongly frustrated Hamiltonian in terms of the true quasiparticles, and the true quasiparticles are non-interacting. So even though we're going to focus on low energy features, this mapping is actually true for the full spectrum. So in principle, we can compute anything we want rigorously. Okay. Good. So let's look at what happens if we put this on a honeycomb model. So now we have this free Majorana hopping problem on a honeycomb model. This is the phase diagram that you get. So what do you see here? You see that we have three different coupling constants. We allow them to vary. And we find that there are two different types of phases. So if one of the coupling constants is much larger than the other two, then we're in the blue regions of the phase diagram. And that is a gapped spin liquid. And this gapped spin liquid is actually in the same topological phase as a toric code model. If all the coupling constants are approximately the same, then we're in this magenta region here in the middle, and that is a gapless spin liquid. And what that means is that the Majorana fermions, they have a gapless dispersion, and in this case it's the same dispersion as you find in graphene. So you have the Dirac cones that sit at the corners of the Brion zone. Now, the same thing we can do for any lattice, any tricoordinated lattice, any dimensionality. So let's do that. Let's look at tricoordinated lattices. And I don't want to do it for the whole set of lattice. What I want to focus on is really three representatives that give us three different physics. And the three representatives is what we call 10A hyper octagon, 10B hyper honeycomb, and 8-3B. Just to remind you, this lattice exists in the Iridates. The other two lattices, we believe they exist in the metal organic frameworks. So let's first look at a generic phase diagram. The phase diagram is actually more or less always the same no matter what lattice you put it on. Details may change, but it's always the case that if one of the coupling constants is much larger than the other two, then you're in a gapped spin liquid regime. If they're all approximately the same, you're in a gapless regime. The phase boundaries really depend on the lattice and what you're looking at. So we're going to focus on the gapless regime here, and we're going to ask ourselves what kind of dispersion relations can the Majorana fermions form, and that really tells us what kind of quantum spin liquids can we have. And what you see here is that you have a lot of freedom, so these Majorana fermions can form anything from a surface over nodal lines to wild points. And what you get really depends on the lattice. So what actually sets what kind of physics you get? Well, in general, we would say, okay, what constrains the physics should be the symmetries. And that is true here as well, but with a slight twist. So we started with a spin system. So the physical symmetries, they act on the spins. Yeah, I'll manage. So they act on the spins. So this is the physical symmetries, but that is not the symmetry that is relevant. What is relevant is how the symmetries act on the Majoranas. And when you do that, you have this gauge field floating around. And the gauge field tells you that symmetries can be implemented in different ways. Let's take time reversal, for example. So time reversal, you usually think that it relates the Hamiltonian at k to a Hamiltonian at minus k. And so that's the relation you're all used to. And if time reversal is implemented like this, then you always get a gapless spin liquid with a nodal line. The point is, it doesn't have to be implemented like this. It can be implemented differently, namely with an additional translation in momentum space. So this vector k0 here, that is half a reciprocal lattice vector. And depending on this lattice that you look at, this k0 is not 0. And if it's not 0, then you generically go into this case, you will stabilize Majorana Fermi surfaces. If you want to have Weil nodes, then you need an additional symmetry. In this case, it was inversion symmetry that basically tells you that this Fermi surface up here is not stable. In fact, only point nodes can be stable. Good. So that is the physics for the pure Kitaev model. So let's perturb it. Let's go beyond Kitaev interactions. Any material will have something else like Heisenberg or anything that is symmetry allowed. So what happens if we put in these interactions? Now the first thing I want to stress is that you have a finite range of stability for the quantum spin liquid phase because of the gap in the flux excitations. So that is what protects the quantum spin liquid. But of course the nature of the quantum spin liquid could change. So here you see that if you look at the effect of Heisenberg interactions, well, they will get interactions between the Majorana fermions, and these are arbitrarily irrelevant for lines and points. Here, so you're safe here. They're marginal for Fermi surfaces, and of course, when you think of a Fermi surface and interaction, you think of BCS, and that's what happens here. You have a BCS instability. It will not destroy the quantum spin liquid, but it will destroy the Fermi surfaces, and it will leave nodal lines left. So you're going to a nodal spin liquid. The other thing you can do is you can put magnetic field. This is again completely harmless to Weil nodes. It's actually beneficial for the Fermi surfaces because it deforms the Fermi surfaces and will cut off the BCS instability that you got from interactions. So in a magnetic field, a quantum spin liquid with a Fermi surface actually has also a finite stability. It's harmful to a nodal line. A nodal line gets generically broken up into Weil points. So maybe one take-home message from this slide for the expert is that 3D spin liquids really want to be gapless in contrast to 2D spin liquids. And you generically get 3 different behaviors: Fermi surface, a nodal line, and Weil points. And depending on how you, which symmetries you have and which lattice, you get into these 3 different regimes. So this is an overview plot over the lattices that I showed you earlier. Let's color code it to have a slightly better picture. So red is Fermi surface, blue is Fermi line, green is Weil nodes. And you look at this thing, it looks absolutely unsystematic. It looks like anything can happen. That is not entirely true. If you really do a proper projective symmetry analysis, you see you can explain all these phases and what happens if you break time reversal or if you introduce interactions by using the projective symmetries. Now I have 2 comments for the experts, and that is the Weil nodes that you get here for 2 different lattices, 9a and 8b, in presence of time reversal. Now, these 2 lattices are special because they not only has the Hamiltonian time reversal, but it also has inversion symmetry. And for fermionic systems, there's a no-go theorem. You can't get Weil nodes if you have time reversal and inversion. Now, for quantum spin liquids, you can. In the first case, what happens is you spontaneously break time reversal symmetry because you have odd length plaquettes. And the second one, you really have both symmetries, but they're implemented projectively, and that lets you have Weil nodes. Of course, this was time reversal and inversion. If you introduce other symmetries, in particular non-symmetric symmetries, you get much more. For instance, you can get spin liquids with Dirac points, or you can get nodal chains. And with that, I'm with my conclusion. So I hoped I could convince you that Kitaev spin liquids really have interesting physics. You can got all kinds of different quantum spin liquids with different gapless band structures. It's exactly solvable, which means that we can compute a lot. In particular, we can compute rigorously what are the experimental signatures of these quantum spin liquids. And what you have specific heat, neutron scattering, Raman scattering, thermal Hall effect. We can compute the signatures for all these things and predict what you would see in experiments. Now, this is where we stand now. What we of course want to do is we want to use these exactly solvable Kitaev spin liquids to not just look at this exactly solvable point where we can compute exactly, but also to go away from the exactly solvable point and realize, okay, what are the more generic features if I have all kinds of interactions. So you really want to look at finite strength interactions. You want to know what the flux physics is, because the flux physics now is going to be dynamic. It's going to be much more complicated. You also want to know what happens if you put disorder and dislocations in the system. Principle, you have interesting features there. And if you want to read further, then read any of these papers. There's a lot coming out. So with that, I want to thank you for your attention.
Thank you.